Hello, today I would like to introduce you the VSA functionality to show you how powerful the VSA could be on very complex modulation signals. At the moment, we are generating a radar signal that has been captured on the field thanks to the VSG, which is in our product. We are generating the file physically onto the VSA, a kind of loop, and so the signal is being played in a loop all the time. At the moment, we are looking at the spectrum analyzer on its own, which is a swept spectrum analyzer. As you can see, it's not that easy to understand what's inside this signal. So for sure, we can play with the trace and have a different one and try, for instance, to get a Maxwell to understand about the shape, the envelope of the signal. But that's pretty everything you can do. If we stop that one, go back to the trace A, sorry, and then go to span 0. For sure, we will have to change the time. We will have to change the RBW. What we understand from this screen is that without any trigger that we can change for sure, we understand that there are pulses. There seems to be one pulse which is wider than the next one, and then the wider, and then the narrower, and so on. But that's pretty what the spectrum analyzer can do. For sure you can check about power of each burst and so on, but that's it. So now let's focus onto the VSA of the same signal, but being analyzed in a different way. I switch on to the VSA. I'm generating the same signal. At the time it's so fast that you can't see it moving. We are analyzing the signal. At the moment you can see the spectrum being analyzed, displayed. We can see the shape. It's much more stable since we are looking at it for a few milliseconds, like 2 milliseconds long at the moment. So what I will do is I will try to show you how powerful is the VSA when we will be adding a second trace, a subtrace, like power versus time, to really understand what's inside the signal. So at the bottom of the screen you can see the pulses. We can make a kind of zoom in of the blue zone will become the bigger screen. So let's come back to the top one and make it, instead of the spectrum, let's make it power versus time to try to understand, so that we have exactly the same information on both windows. And then I will make this blue zone smaller, just to focus onto 1 or 2 pulses only. So I will decrease the size of the blue zone, and I will first focus on the first pulse. I can make this zone moving. I can then focus on the smallest one, so we can easily see that these are really different widths of the burst. So let's focus, let's say, on the third one. I will try to make it bigger, just really to understand what's inside the burst. I will decrease the blue zone width, so we have to manually adjust to understand what's inside. Let's say we are happy with this. So the blue zone you see on the screen is exactly what you get on top. So at the moment we are looking at power versus time, and now thanks to the VSA we can get different domains that can't be seen on a spectrum analyzer. Let's go to the frequency versus time. This is pretty new and not anything you can show on a spectrum analyzer. So as we see on the screen, so this is the noise, this is the width of the burst, this is the noise again, exactly what we are looking at in the blue zone. And inside the burst, I now understand that there is a frequency inside. So what I can do is I will be using a marker. I can change the marker position just to understand about the frequency inside. So let's go to this state here. We can see that I'm generating the signal at 3 gigahertz, and it tells me that the frequency inside is very close to 3 gigahertz. So we are getting the exact same carrier in this burst. So the widest burst seems to have 3 gigahertz inside. We can see some transition steps, transients inside the burst, and we will in a few seconds understand why. Let's go down to a different trace. Let's go to the phase, just in case there is any phase to see. We can see, so I can stop the screen just to not to get it moving too much. We can see that there are steps inside, so there is phase modulation inside this burst. I can use again markers, and then I will have a look at the second marker, which is on the right by now. Let's go to the bottom of that. I can see that there is a difference of minus 179.64 degrees. So this phase modulation really is being carried inside the burst. At the same time, it's being carried at 3 gigahertz Gaia. This is an interesting information. I can have a look also at the so-called spectrogram. What it does, I will switch off the marker. It shows you the time of the capture, so really the blue zone. This is the frequency I'm having a look at. So at the moment it's 50 megahertz vertically speaking. And then I have a kind of a 3-dimension color-coded amplitude. So I understand about how the spectrum or the carrier behaves when it's from the noise and then going to the burst and then going back to the noise. So what we see is that it confirms when we have the highest amplitude, it confirms that when I am in the middle of the screen, vertically speaking, I'm at 3 gigahertz, which is the center frequency of the VSA as well. So now let's focus onto the narrower burst. So I will now move to the very small one. So let's go back to trace mode, and instead of having the spectrum of this single burst, I will go to power versus time, and I will move the blue zone to the other burst. I will again have to manually adjust to get something pretty easy to understand on the screen. So since the burst is smaller, I will decrease the size of my window. 10 microsecond, 9, 8, let's say 6 microseconds. So this is my narrow burst that is being analyzed at the moment. I can see the amplitude, I can see some steps again, transitions inside. We will try to get the same as with the widest burst. Let's go to frequency versus time. What do we see at the moment? So we have still the same information. This is frequency, this is time. And at the moment, rather than getting the signal in the center as we had on the widest burst, we have the information, but maybe below, which makes me think the frequency that is being carried by this burst is a little smaller than 3 gigahertz. So let's move the marker number 1 to the step over here. It tells me 2.989 gigahertz, which is 10 megahertz below the center frequency of the VSA. This is one important information to keep in mind. Let's try now to understand about phase. Is there any phase modulation in this burst? As you can see, it is getting crazy. So no way to demodulate in case there is anything to demodulate in phase. Well, I'll come back to this shortly. If we go to the spectrogram shape, again, this confirms me that this frequency contained in the very small burst is below the center frequency. So now, since I would like to better understand about phase, I will go and change the center frequency of my VSA. I will not change the signal on its own, I will just change the center frequency. So let's go back to spectrum just to let you see. I will just focus on the same burst, but I will just change the frequency. So rather than 3 gigahertz, I will go to 399. gigahertz, 2.99. As you can see, we can still see the bursts. I've just changed a bit the center frequency. I can again go to power versus time. I'm still focusing onto the small burst. I can have a look at frequency versus time by now, and what is the difference compared to before. Now the center frequency is 3.9, let's say 9 gigahertz. So now the center frequency inside this burst corresponds to the center frequency of the VSA. So this should normally allow me to demodulate the phase in case there is any phase in the burst. Let's go to the phase versus time by now. What do I see now? If I stop it, I see steps inside the same burst, this small burst, and I can again move, let's say marker number 2, to go to the next step. What does it tell me? It tells me between marker 1 and marker 2, once again I'm having 179.88 degrees difference. So in this modulation, I understand in this burst that there is a kind of code that is being transmitted by the radar. Let's go back to the live signal, and let's go now to the spectrogram. The difference compared to the previous analysis is that now, again, I'm confirming that I'm getting this frequency being carried by the small burst in the middle of the VSA, so it's being really the same. If now I go and I take a wider zone, a blue zone, I will take it wider just to let you see a few differences. I will take, okay, these numbers of slide of burst. Let's get this. So no more markers. What do I see? I'm starting with a small burst, and then a bigger one, and then a small one, and then a bigger one, and so on. I'm getting informations on the screen telling me the exact same thing about center frequency. Then I can use marker just to verify, but I see the burst in time. When it's dark blue, it's noise. When it's getting yellow, orange, I'm getting some signals, and I can see the transitions. So thanks to the VSA, I've now understood that on the small burst, there is a frequency that is being carried at 3.99 gigahertz. On the biggest burst, there is another frequency which is at 3 gigahertz in my example, so 10 megahertz above. And if I correctly set up the center frequency of the VSA, in case there is any phase modulation inside, I can demodulate the phase. So in this example, practical example and true example, we have verified that we can understand about the phase modulation on both bursts at the condition that we know or pay attention to the fact that the frequency carrier that is being inside each burst is probably not the same. So in that case, the widest burst is at 3 gigahertz, and the narrow burst carries 3.99 gigahertz. So this is very important, and thanks to the VSA I've understood this, which is not anything I can do with the spectrum analyzer. So thanks for watching, and I hope you find this video interesting.